All right, we're going to take up the idea of hybrid orbitals today. These are going to be important as we begin to try to explain the shapes of molecules, which will help us to understand how certain reactions take place, why properties of various compounds might differ. Often we can explain that by the fact that the molecules just have different geometries or shapes, which will influence what they're able to do or not able to do. So let's take a look. So as we start to think more about chemical bonding, right, we have Lewis structures which tell us we can figure out where the bonds should be, how many electron pairs should be shared, things like that, right? Lewis structures are good at counting electrons, all right? If we want to think about how those bonds are formed, they're formed by electrons interacting with one another, electrons interacting with the nuclei, right? The electrons in atoms occupy orbitals, and so we want to think about bonding as happening by an interaction between orbitals on different atoms, or an overlap of orbitals is a word that gets used a lot for this. Okay. I talked about this a little bit in the video that introduced ideas about bonding when I talked about making H2 out of two hydrogen atoms, right? If I have a hydrogen atom over here, 1s, 1 electron configuration, its 1s orbital is just a sphere. I have another hydrogen atom here, so I have another spherical orbital. If those atoms come closer and closer together, eventually the two orbitals are going to be able to overlap, right? Because the orbitals, remember, they're not like hard things like bowling balls or anything like that. They're just electron clouds. And so I can get where the electron density from the two atoms is overlapping in the middle. That means electrons in that area can be attracted to both nuclei. That'll lower the total energy, and that's what makes the molecules stick together. Okay, so for hydrogen, that's pretty simple. There are a few other molecules for which that's relatively simple. Okay, one of those illustrated here would be something like HF, hydrogen fluoride. Right? Hydrogen still has its 1s orbital, so I've got my 1s spherical orbital. My fluorine, the valence orbital that has a single electron in it, is a 2p, right, which has this sort of longer, elongated look, right, because it's got a lobe on each side and that dumbbell shape like in the picture. But still, if these come together, I can get an overlap between the electron cloud from the end of this p orbital and that s orbital and make a bond, right? Essentially, that corresponds to just pulling these things closer together, so the yellow s orbital here would sit on top of part of the blue p orbital. In Lewis structures, again, it looks like, I could sort of just imagine snapping the atoms together, right? My hydrogen has a single unpaired electron there. My fluorine's got an unpaired electron in one of its p orbitals. And so like Legos, they could go together and make a bond. That turns out this kind of explanation doesn't work for very many molecules, okay? It's quite limited how many things we can do that way. Another problem with this is if I'm making molecules where the central atom is using p orbitals for its valence electrons, which is true for a lot of important molecules, right? Because carbon, nitrogen, oxygen, those things make a lot of molecules. And they all have unfilled p orbitals in their valence configurations, right? P orbitals are perpendicular to each other, right? So I have x, y, z directions. That suggests I'd expect a lot of molecules, all the organic molecules, for example, to often have 90-degree bond angles if I was just sticking atoms on the ends of those p orbitals. And in fact, those 90-degree bond angles are pretty rare. They're not nearly the most common ones we see, right? Experiments show us that other bond angles are much more likely. Then there are molecules like methane, CH4, right? Carbon's electron configuration, its valence electrons, right, is 2s2, 2p2. So if I picture this as just like snapping atoms onto things where I have partially filled valence orbitals, that carbon atom has two of its p orbitals that each have one electron in it. So that might suggest in our ideas right now that we'd expect CH2 to be a molecule that we'd see. But in fact, CH4 is. And in CH4, all four of those bonds are identical, right? That's not something we can easily explain in terms of using the s orbital and the p orbitals to make bonds. So I said we're going to talk about and use these ideas to explain the shapes of molecules. I want to first take a moment to just talk about how we know the shapes of molecules, right? This is one of those cases where I'm going to tell you I know that a particular molecule is this shape. And that should really make you want to ask, like, well, how could you know such a thing, right? Molecules, after all, are really small, right? And so the way we can actually measure the shapes of molecules goes to, it's related to how we figured out things about energy levels for atoms by doing spectroscopy. It turns out molecules have energy levels as well. And in particular, for knowing the shapes of molecules, the ones that are important are the ideas that molecules actually have energy levels associated with how they rotate. And so you can get a molecule to absorb a photon, typically of microwave wavelengths, that will excite rotational motion in the molecule. And when the molecule is rotating, it turns out you can measure its moment of inertia, or its moments of inertia. And if you've taken a physics class and looked at things like angular motion, you'll know that if you change the shape of the molecule, it'll change the moment of inertia, right? If I arrange the masses in a different way, then they'll spin differently. And so that's how we can measure these, is by watching how the molecules rotate. Okay, and by doing that, we can measure the angles between the different atoms, the angles where the bonds are with respect to one another, and we can also measure the bond lengths, because that would also affect the moment of inertia. Okay, molecules are kind of great for doing moments of inertia because they're really like how physicists like to do things, right? In a physics class, if you talk about the moment of inertia, you start off by saying you have 2 point masses and they're connected by a massless rod or something like that, right? Molecules are really close to that because almost all the mass is in the nuclei, right? The electrons, which are the bonds, that's what amounts to the rod holding them together, their mass is very, very small. And so a molecule is a very good approximation to that sort of standard physics representation of the problem. So that's how we measure the shapes of molecules. Once we can measure them, we want a model that would let us just say, like, if I scribble down a molecule, can I tell what shape it should be without necessarily having to measure its shape? And what I need to do that is just to have measured enough of them that if I get a system that gets those right, I can believe it will get right the ones that maybe I haven't looked at what the actual data say. So I'm going to start by talking about methane to motivate this. Methane is CH4, and if we measure the bond angles and bond strengths in methane, we can see that the 4 bonds are all identical to one another. Okay, they have the same length, meaning the distance from the carbon to each of the 4 hydrogens is the same energy, meaning if I wanted to break a hydrogen off of there, it will cost me the same amount of energy no matter which bond I break. Okay. In the shape that is shown there, that is the so-called tetrahedral geometry of methane, it turns out the angle, if I go from one of the hydrogens through the carbon in the center to another hydrogen, so like this angle here, that angle turns out to be 109.5 degrees. And that's the angle no matter which one of the 4 I measure. Okay, the picture has some perspective going there, which maybe makes it not entirely obvious that's true. That 109.5 degrees is the angle in what is known as a tetrahedron. If you were a geometer, you would recognize that, that particular angle. Tetrahedron is the shape we would get if we put faces on this, right? So if we took the triangles where I take, say, this set 1, 2, 3 of the white atoms, and I put a triangular plane there, and I did that for the 4 possible combinations of them, I would get a tetrahedron. Okay. There's no way I can get to that shape if I say what I want to do is I want to hook those hydrogen atoms onto p orbitals or even an s orbital and p orbitals, right? Because the p orbitals are perpendicular to each other. Okay, so because that's the shape methane is, we have no choice but to mess around with our understanding or our model of things to get a model that can explain how we could get a molecule that is this shape. Okay, we do this by creating what are known as hybrid orbitals. This is going to seem pretty abstract because it is abstract. Okay, so bear with me and I'll try and make sense of it. So this idea of hybrid orbitals is a patch to the way we talk about bonding, to our thing that we want to just imagine hanging the hydrogens on an orbital that comes from the carbon. Okay, we do this because we want to match the observed facts that methane is that shape. Okay, I need 4 identical bonds on carbon, so I need to get to have 4 identical orbitals, and I want to have each one have 1 electron in them. That means essentially I want to take the orbitals from carbon and I want to make a new set of orbitals out of them. If you think about the fact that orbitals are just functions, then when I say I'm going to mix them together to make new orbitals, what I'm saying is I'm going to take linear combinations of those functions. Okay, so the smattering of people among you who know some things about linear algebra can maybe begin to visualize how this would work a little bit. Okay, what does that mean? If I have a carbon atom and I've got a 2s orbital and I've got a set of 3 2p orbitals up here, right? When I put my electrons in there, I expect them to look like this. Right? But suppose by playing around with those orbitals, by making these linear combinations, if instead I had a set of 4 orbitals, and these are going to be what I'm going to call the sp3 hybrid orbitals, if those 4 orbitals all had the same energy and I put electrons in them, I put 4 electrons in them, they'd want to go like this. Okay. Now, the energy of these new orbitals has to come out sort of like I sketched it here, in between the energy of the original s orbital and the original p orbitals. It should be closer to the p's because, after all, 3 of the 4 that I'm mixing together are p's, right? And so this is what happens when we make these. When it says sp3, this 3 up here says we're using all 3 of the p orbitals. I take 4 orbitals and mix them together. I have to get 4 orbitals back out. So sp3 orbitals are always going to come in a set of 4. Okay, that's confusing. Let's take a look at how this would work for a simpler case. An easier case would be if I wanted to make sp orbitals, okay, which I can also make. So this is going to be an sp hybrid. That means I'm taking the s orbital and just one of the p orbitals and mixing those together. In these pictures, the sort of greenish dot in the center of things here, that represents the nucleus of my carbon atom here, say. And this dot over here represents the same nucleus of the same atom, okay? So these are 2 orbitals from the same atom. The coloring of the orbital represents the sign of the wave function, which is actually important for this part, okay? The s orbital, the wave function is positive everywhere. In a p orbital, the wave function sign is positive on one side and negative on the other, okay? We've kind of skimmed over that because it's not important for much except for this. If I take these and I make 2 combinations, 2 linear combinations of them, if I add them the way I've got them drawn there, then on the left-hand side, my electron density will go up, because if blue is the positive sign, where blue gets laid on top of blue, imagine now that I take the green dot from there and the one in there, and I lay them on top of each other, right? On the left side, I have blue on blue, and that's going to make it grow. On the right side, I have blue on red. Blue is positive, red is negative. So when I add those together, it's going to shrink, right? And so I end up with an orbital that looks more like this one. So this orbital now, instead of looking like a p orbital, which is kind of pointed both ways, this one is pointed very much in one direction. Okay, I guess it's pointed in the other direction. Sorry about that. But then my hand isn't in the picture. If I take the one on the bottom, just change the plus sign to a minus sign. Now, when I put blue on blue, that's the same sign, and I subtract them, that's going to reduce the electron density, right? And so I end up with an orbital that looks just like, that looks just like the one above it, but now it's pointed in the opposite direction, okay? So if I take my s orbital and one of the p orbitals, combine them, I can actually get this new pair of orbitals that just the only difference between them is they point in opposite directions, okay? Those are called sp orbitals, and they'd be perfect for making bonds on, right? Because they point in opposite directions. I could put an atom on one, an atom on the other, and I'd have my 3 atoms then would all be in a line. Okay, that's how this works. If I wanted to make the sp3 hybrids, I'd have to do that, but using 4 orbitals to mix together. And then I'd have 4 combinations, because I'd have one that was plus, 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 and one that was plus, plus, minus, and so on. I would just change one more sign each time to get the different combinations. It's much harder to visualize that because it has to be 3-dimensional then, where this one obviously works in 2 dimensions because everything is along the same line. So if I make these sp3 hybrid orbitals, which is the version of doing that would involve all 3 of the p orbitals and the s orbital, again, if you think about this as s1 p3, add the 1 and the 3, you get 4. That says these are going to come in a group of 4, okay? They're going to be pointed in the directions that get them as far apart from each other as they can get. In this case, it turns out that is that 109.5 degree angle. That is the maximum separation that I can get if I have 4 directions and I want to just get them spread out in space, okay? That matches the shape that methane happens to be, right? If I make those orbitals, I have 4 identical orbitals. I put 1 electron in each of them from the carbon. Then I can imagine the hydrogens coming up, and the s orbital from the hydrogen overlaps with the big end of each one of those 4 orbitals. It makes a methane molecule, and it explains why the methane molecule has the particular shape that we experimentally can tell it does, right? So again, this is sort of the pragmatism of science. It says that, well, we have these atomic orbitals and they don't quite work for explaining molecules. What that means at a deeper level is that when the hydrogen atoms approach the carbon, the forces going on between them are strong enough that it actually is able to sort of mess around, if you will, with the electronic structure of the atom, right? So those orbitals are getting rearranged, not just because like we wanted to do some math, but because when the other atoms are present, there's a different set of forces. And what the electrons are doing is they're just always finding their way into the positions that get them the lowest total energy. Right? Electrons are really good at just knowing the right answer and making the most stable form of the molecule. We just do our best to make models that try to explain that. So turns out we can do this if we do the S and the P like I drew the picture for, we get SP. If I use two of the P's, I get SP2. The SPs are going to point 180 degrees across from one another. The SP3s, we looked at that a moment ago for the methane. Those have that 109.5 degree angle, which is harder to draw. The SP2s would actually point towards the corners of an equilateral triangle. And so the angle in here would be 120 degrees for all of them, right? Because that's taking the three directions and getting them as far apart from one another as possible. So that's what we're going to use to begin to explain the shapes of molecules. Okay, I close with a little table here. I introduce here for the first time, and I'll talk about this more in the next video, the idea of the steric number. Steric number, for now, I will say very loosely speaking, that's just the number of directions in which something is poking out from my central atom. Okay, if there are two directions poking out from there, then that will lead me to expect to see these sp hybrid orbitals because those point 180 degrees across. Then a molecule that's based on that, I'll expect to be linear. Right? SP2 says I have three things sticking out, steric number of three, my fancier way of saying that. Trigonal planar is the chemistry book word for saying the molecule has atoms at the corners of an equilateral triangle with the central atom in the middle. And again, if I have four directions, then I get my sp3 hybrid orbitals and my tetrahedral shape like we started off with for methane. In the next video, we'll look at variations on those shapes and how we can explain those.